Hello, we are Team 5. We will start presentation about Burj Khalifa. We're gonna talk about role of team members, weekly plan, summary, monitoring system, preview of next week. This is role of team members. 하상원, 최현준 take a role about research and arrangement. 변상구 takes a role about research and writing script. 이진우 takes a role about PPT planning and making. 장민지 takes a role about PPT designing and making. And Shin-Young-tae takes a role about presenter. In last week, we presented load measurement. This week, we will present the monitoring system used in construction to manage the load. This is summary. Last week, we presented the load applied to the building and the new structure to support building. The loads applied to the building were axial force and lateral forces. By using the structural system in Burj Khalifa, they developed and used the buttress core, the latest technology used in Tower Palace 3, for the reason of Dubai. In the buttress core, the corridor wall and the hammerhead wall act as an outrigger to connect the core wall and the outer wall and act as wing. 3 wings placed around the core support each of the other 2 wings. When the outer end of the outrigger rotates, core wall resists the moment. In other words, effectively resisting not only the axial force but also the shear force and moment generated by wind. In addition, exoskeleton and setback timers were used to resist wind blows. However, while it is novel that the structural system was included in the design, the tower's construction plan was very difficult in every way. Because it's a tall building, if there is difference 1 degree on the ground, it can cause 40-meter difference above the 800-meter. Even if there was a slight error, the displacement of building in the top was very different, which is very dangerous factor. Thus, that is sensitive to load. Many attempts have been made to design a safe building through these techniques and methods. More accurate and precise information was needed to use these technologies, and various monitoring programs were used to check the building's conditions and structure. People exhausting the world, monitoring system in 1990, John Hancock Tower located in Boston measured and monitored buildings in situations where their performance was suspected. Starting with John Hancock Tower, full-scale monitoring applications have begun to flourish as the need for life safety and rapid re-inspection in high-earthquake areas increases. However, these monitoring systems were wild systems, making them difficult to apply to skyscrapers. That is when sensors are distributed across large and complex structures. They become less practical as they go on full scale. Soon, a lot of technological advances put the radio system in place, but the problem was that there can be interference of radio frequencies. Through this process, a unique system called the Smart Sync, which minimized the limitations of architecture while taking advantage of the architecture, was introduced and applied to Burj Khalifa. However, there were difficulties in applying the monitoring system to Burj Khalifa. Total stations or instruments that receive signals from the points required for investigation, and as the height of the building rises, the distance between the highest point and the total station has become too far away to be precise. In addition, accurate measurements have become more complex due to the building's movement during construction. Therefore, the need for extensive survey monitoring programs was essential to provide accurate building locations at specific points in time with respect to design locations, and to ensure the exact location of entire station. Overcoming the difficulties described, the development of extensive monitoring programs for all building elements affecting movement was required. A new measuring system has been developed that uses the latest development of Leica geosystem in combination with precision slope sensors and has been deployed every 20 floors. The precision slope sensor is Cliometer. It is an instrument that measures the angle of sloping, tilting, and angle of descent of an object with respect to gravity. The main purpose of the monitoring system with this function is measuring lateral movement. These are detailed examples about lateral movement. 1. Measuring the total strains and continuously measure it so that it doesn't deviate from the design value. 2. Checking column sharpening. 3. Ensures stability by identifying dynamic characteristics, for example, frequency, damping, during construction, ultimately to ensure the stability of the building. The kind of monitoring systems that are designed to achieve this objective is SMP, Strain Measurement Program, SHM is present. Let's look at each of the next slides. First, the Survey Monitoring Program is a monitoring program that prevents problems that occur during construction. SMP used in Burj Khalifa where survey of the tower's material movement during construction, column and wall shortening survey. First, SMP was used to position the sabatier. Last week's presentation, we showed that the development of the buttress could solve the load problem. The sabatiers were the most important issues considered in the initial design and construction phase. SMP tracked the reduction of columns at all setback levels and predicted the reduction of columns within the predicted range. Also, used to prevent the building from tilting during construction, the SMP monitored the tower's lateral movement every day to track the tower's movement and make necessary corrections. In addition, this analysis was performed regularly to compare actual measured lateral movements with predicted lateral movements, such as during construction of the building, immediately after completion. Next, to measure the column reduction and lateral movement of the tower, the strain measurement program was developed to measure the total deformation of the walls and columns due to elastic shrinkage and creep. SMP normally is placed in a deformative area, but SMP is placed below outrigger where large load redistribution is expected. Strain gauges were installed throughout the building. Pressure load cells were installed in the foundation. The strain measurement was compared with the predicted strain of the building through the construction sequence analysis model. This was from the time the strain gauge was installed until the building was completed. Lastly, let's talk about SHM. Structural health measurement is a damage detective system used primarily in civil infrastructure. By using cliometers, it can periodically update information about aging and deterioration in the building environment and whether the structure can perform its intended functions. Therefore, SHM can install GPS antennas on the roof of the building to predict the damage or find and repair the damaged area directly through SHM after an extreme event. The SHM used in the Burj Khalifa are a temporary SHM and a permanent SHM. We'll tell you about them. Temporary SHM was developed and installed in Burj Khalifa in cooperation with Notre Dame University. It was responsible for monitoring the acceleration of buildings, measuring displacement, and providing real-time feedback on tower dynamic characteristics and behavior during construction and before construction of structures. The permanent SHM can perform measurements such as building acceleration, movement, slope of the base of tower, and fatigue behavior of steel structures. The program also included weather stations measuring temperature, humidity, wind speed, and direction at 138 levels. Permanent SHM measures the predicted behavior of building from the above measurements, indicating that the predicted values and measurements were very similar when a 5.8 magnitude earthquake hit southern Iran on July 20, 2010. Let's summarize what we can get from these monitoring results. 1. Feedback on all the lateral loads of the tower to provide construction period elasticity of the model. 2. Providing sufficient data on fatigue behavior of steel structures. 3. Checking the speed and distribution of wind. 4. Providing immediate information to the facility measurement team. Also, if there is difference 1 degree on the ground, it can cause 40-meter difference above the 800-meter. So the Burj Khalifa was constructed with a correction error of 5 mm or less. Additionally, due to the weight of the building, Burj Khalifa expected to shrink by about 65 centimeters after completion. Experts didn't miss this, and each floor was designed and constructed 2 to 4 mm high in advance. This is the best calculation and measurement techniques. So far you've seen the overall content of load measurement methods and their associated monitoring systems. In addition to these problems, we needed to prevent problems caused by disasters. Next week, we'll learn how Burj Khalifa can overcome the challenges of the disasters. This slide is our last slide. Thank you for listening.